The truth set of a statement containing a single free variable x, p of x, is just the set of all x's such that p of x is true. This is the truth set of p of x. For example, if our statement was p of x equals x is 7 years old, then the truth set would be the set of all x's such that x is 7 years old, or in other words, just the set of all 7-year-olds. What this means is that every element in the set of all 7-year-olds inputted into this statement makes this statement true. So if John is 7 years old, then if you input John for x, John is 7 years old would be true because John's 7. But then how do you do a truth set for a statement containing two free variables like this? One intuitive way of doing this, it's wrong though, but one intuitive way of doing this would be taking the set of all x such that p of xy and then doing the union with the set of all y's that make this true. But then if the truth of p depends on x and y, you can't just assert that a statement is true if you only know one free variable, because there's another free variable, because it depends on two variables. So you can't do this. We need a new tool that encodes the information for the truth of this statement. Can't just do single values. And that's where we introduce ordered pairs. The definition of an ordered pair is really simple. It's a really easy concept to grasp because you've already grasped the concept before. I mean, if you've done like any type of programming before, you've already seen it's called a tuple, but especially like in C and Python and stuff. But this is an ordered pair. All an ordered pair is two things separated by a comma and surrounded by parentheses. And this looks familiar because you've already dealt with ordered pairs before. Like, this is a point in the xy plane. Look at this. Imagine this is the xy plane, right? And then say this is the point 2, 3. There you go. You've already dealt with this before, but in this video we're just going to generalize it to other use cases, not just graphing. So imagine the statement, So for example, let's take this statement. P equals, P has C children. So for example, Donald Trump, comma 5 would, this ordered pair would make this statement true. But if you did like Donald Trump 4, then it wouldn't be true because Donald Trump has 5 children, not 4 children. In this statement, P ranges over the set of all people, and C ranges over the set of all integers, or not integers, natural numbers, because you can't have -1 children or something. Alright, so P ranges over the set of all people, and C ranges over the set of all naturals. You could do the set of all naturals if you could do the set of all naturals union set of 0 if you don't consider 0 a part of the naturals, if you're like weird. Anyway, what I'm trying to say here, the only types of ordered pairs we should consider PC is if P is an element in the set of all people and C is a natural number. So if you did like 5, oh crap, what the hell was that? 5 and then Donald Trump, then that wouldn't make any sense because 5 has Donald Trump children. Like, what the hell are you talking about? So all the ordered pairs that we have to consider must make the sentence have some meaning, because if you input 5 Donald Trump into this for PC, then it doesn't make sense, but inverse it, yeah, whatever. So in general, if we have some statement P of x and y, and x ranges over A and y ranges over B, assuming A and B are sets, of course, then the only assignment of values that we should consider for this, for x and y, or for this ordered pair, would be if x is in A and y is in B. Now this leads to the following definition. If we let A and B be just any set, then the Cartesian product of those sets, the Cartesian product denoted A cross B. This is really similar to cross product of vectors, but it's not that similar, but it's similar in notation. Anyway, it's just a set of all ordered pairs A comma B, such that A is in A and B is in B. So, for example, if A was a set of of 1 and 2, B was a set of 3 and 4, then the Cartesian product, I'll just read it as A cross B for convenience. Then this set would be the Cartesian product, and we can put anything, literally anything in these ordered pairs. So we could put colors, so still works as long as it's an element. We could do like A equals freaking this and that, and B equals, literally just any set, and that includes the XY plane that we all know. So let's say X is just the real numbers. This is what this number line is. This is what the x-axis is. And then y is also the set of real numbers. So we generate the xy plane with doing x cross y, which would be r cross r. Or another way you could do that, you could write that would be r squared or r2. I say r2 because it sounds better. I don't know. This graph of the xy plane is possible because of Cartesian products. This entire plane, the entire xy plane, represents every point visually, every ordered pair in R2 visually. It visualizes it. All right, so this leads us to our first theorem, I guess, which is all these 5 properties for all Cartesian products. In this video, I'm actually just gonna prove 1, 4, and 5, because those are the most different ones to prove, I think. Alright, let's go to the first one. Alright, so the first part of this theorem states that the cross product between a set and an intersection is equal to the intersection of that set, that alone set, with each of the sets that are being intersected together. Well, one way to prove 2 sets equal to each other is to let x be any, just let x be arbitrary, and prove that x being in one set is logically equivalent to saying that x is in the other set. So if we can get this, we can prove that they're equal to each other. Alright, so first we have to let x be arbitrary, of course, because we want to prove this for all of the elements. And then we try to figure out what is this statement equal to? What is x is in A cross B and C equal to? Well, first off, we can just rewrite this cross product as this set using the definition of a cross product. See where we go from there. Since x is an arbitrary ordered pair, all this is saying is that there must be at least one element in A and one element in B and C, such that x is equal to AB, this ordered pair AB. So what we get is that this statement is equal to this statement, and I'll just expand this, turning this statement into this statement. And now what we'll do is split the single value x. We'll just notice that it's an ordered pair since it's in a Cartesian product, and split it into 2 values, x1 and x2, for x1 being first coordinate, x2 being the second coordinate. So now what we'll do is just rewrite this statement, but make x1 equal to a and x2 equal to b. So, and that's the same thing as making x equal to ab. Alright, so I've rewritten this as this, and what I've done here is take this conjunction in the parentheses out the parentheses with the conjunction of existential statements themselves. What this is saying is that there's an element of A and an element of B, such that x1 is A and x2 is B, and there's an element of A and an element of B, or element of C, sorry, element of C, such that x1 is A and x2 is that element in C. Now what I've done is replace the bound variables for another bound variable when instead of A and B it's C and D, because it's saying the same thing because they're bound variables. It doesn't matter what they're like. It doesn't matter what what their name is. It can be X, it can be Y, it can be C, H, whatever. And these two statements are logically equivalent because x1 and x2 only have one value. So that's the reason why we can do this. And if we let the A, B, C, and D that satisfy these conditions be in A, B, and C, respectively, where A is in A, B is in B, C is in A, and D is in C, this whole thing can be collapsed down to A is equal to C and B is equal to D. Alright, keep that in mind for that is what this statement is equal to. Alright, so now, since we have that, now we need to figure out what this union, what saying X is in this union is logically equivalent to. Well, first off, we can just, split this off into two membership statements with the conjunction, because by the definition of an intersection. Alright, now I've rewritten the separate parts of the conjunction as existential statements. So for example, this one would be there's an element of A such that there's an element of B such that X is the ordered pair AB. And I've also done that with this part too. Alright, so here I've just expanded X equals the ordered tuples, or not ordered tuples, ordered pairs, into conjunctions too with coordinate-wise equalities. And what we'll do, let such an A and a B that makes this true, this equal A, this equal B, and such a C and a D that makes this true, equal to C, equal to D, respectively. And that gets us this. I don't want to circle that. I meant that gets us this. And finally, we have that is logically equivalent to this statement right here. And this is equivalent to this, not just because it's the same variables and same symbols, but because the variables represent the same things because we're talking about the same X. And since, as we've shown, that if we let X be arbitrary, that X being in this A cross B and C is logically equivalent to saying X is in A cross B and A cross C. That means that every element in this set is also in this set, and every element of this set is also in this set. So that means that these two sets are equivalent. And now we move on to the fourth statement in the theorem, which says the union of two Cartesian products is a subset or equal to the Cartesian product of the union of those corresponding sets. So we're going to prove this by showing that every element in this set is in this set, but not every element in this set has to be in this set. First, we have to let X be arbitrary, of course, and we have to figure out what the hell it means to be in this set. Well, we can just separate this union here with a disjunction between X being in this set and X being in this set. since that's the definition of a union. And here we'll do the same thing we did before and turn these membership statements into X. And that gets us this statement that says x1 is A and x2 is B, or x1, oh crap, or, sorry, x1 is C and x2 is D. Now, keep in mind that since we're using inclusive OR, it could be the case that these two are both true, in which case A would be equal to C and B would be equal to D. But anyway. Alright, so now we have to keep that in mind. Now we have to figure out what X being an A or C cross B or D is logically equivalent to. Well, obviously turning it into an existential statement would be equal to this. And to make it easier, we'll just split up these union of these sets into separate disjunctions here. And now using universal instantiation and letting A, B, C, and D be elements of A, B, C, and D respectively, we can rewrite the statement. And using the fact that X is an ordered pair, x1 comma x2, we can break the statement down like this. We can simplify it like this. Now this looks really similar to this statement, but it's not equivalent. Let's assume that X is in this first set here. So either x is AB or X is CD. We'll do this case by case. In this first case here, if we take x1 is A and x2 is B, then we'll see that this is true. This is also true, since this is satisfied since x1 is A, and this is satisfied since x2 is B. If you look at the second case, where x1 is C, x2 is D, see that's also true because x1 is C, so this is satisfied, and x2 is D, so this is satisfied. So now we've shown that this is a subset. I don't know how to do it backwards, or not backwards, whatever you want to call it. Sideways. We've shown that this is a subset of this, but now let's assume that X is in this second set. It might seem to you intuitively that these are the same thing, but actually no, because if this is true, then it could be the case that, you know, x1 is freaking what do you call it? X1 is A and x2 is D. That makes this statement false, because if x1 is A, if this is supposed to be true, x1 is A means x2 is B, but no, x2 is D. So this is false. So since there are cases where this is false and this is true, that means this first set is a subset of this set, but this is not a subset of this set. So they're not equal, but this is a subset. So now we finally have that this is a subset of this, or A cross B or C cross D. This is a subset of A or B cross C or D. Also, when I'm talking about sets and I do like A intersect, why did I do D? Like A intersect B. I'm not gonna say A intersect B because I'm just gonna say A and B because it's easier to say that. Same thing with A or B. I'm just gonna say A or B instead of A union B because it's for convenience. And now we want to prove this final statement in the theorem, which says that if you have two sets and one of them is the empty set, their Cartesian product is always, always, always the empty set. For any set A, it could also be empty. One way you could go about this is let X be arbitrary, of course, and let it be an element of A cross empty. And this statement is equal to, there's an A, and there's a B in the empty set, where X is the ordered pair AB. Now you should notice immediately that the empty set is empty, so like it doesn't have any elements. So this part is always, this is a contradiction. This is always false. This whole thing is always false, so there does not exist an A such that this is true, since this is always false. So And since that is always false, saying anything is in this set is always false. So that means this is empty. And here we have the same thing but reversed, which is the empty set cross A. And this is obviously also false. I just didn't want to I just didn't want to finish this because it's obviously false. Because this first existential quantifier is always false. It's a contradiction. Because once again, the empty set doesn't have anything in it. So there does not exist an A in the empty set such that, you know, anything. Therefore, this set is the empty set. So blah blah blah. You know the rules. And I didn't do statements. I didn't prove statements 2 and 3 in this video because number one, that's like too much or something. And then also because I want to leave it to you because I want you to practice with some Cartesian products. So since we know that order matters in Cartesian products and order pairs. For example, if A and B are distinct, then BA is not equal to AB. So from this, we know that in general, this is not true for any sets A and B. So a reasonable question is to ask yourself, is there a case where they are equal? Well, obviously, intuitively, it's true if B is equal to A, and it actually is true. Since A cross B is B cross A, is A cross A is A2. But are there any other possibilities? Well, I'm about to show you a proof that says no. There are no other possibilities. A cross B is B cross A only if B is equal to A. So first, to start off, we'll just assume that A cross B is equal to B cross A. This means that if we let x be arbitrary, then saying x is in A cross B is logically equivalent to saying x is in B cross A. Rewriting this into existential statements, we get this. Over here I used AB and over here I used CD, because if you use AB still, then you can get confused with which A and which B you're referring to. You can get the proof wrong, so I'm just using different variables for each one, just in case to make the proof correct. Using existential instantiation, we can see that this is true, that x1 being A and x2 being B is logically equivalent to x1, x2 being CD. Since we're assuming that A and B are non-empty, since that would create an empty set, x1 and x2 must exist. They must have one value since we're referring to one x, one ordered pair here. So that means A is C and B is D. Since we're letting x be arbitrary, x represents every ordered pair in the set of A cross B and B cross A. So because of that, x1 represents every element of A, and x2 represents every element of B. So what A equals C is saying is that every element of A must be equal to every element of B. Since A is just an element of A, C is just an element of B, as defined here. And then this is saying the same thing. Every element of B must be equal to every element of A. And it obviously follows that A must be equal to B, since that is the definition for equivalence with sets. That's if A and B are both non-empty. If one of them is empty, then A cross B would just be the empty set, and so would B cross A. And in that case, A cross B would be equal to B cross A. But if A was empty and B was not empty, then obviously A is not B. And the same thing happens if B is empty and A is not empty. A cross B would be equal to B cross A, but no non-empty set is equal to the empty set, so it would not be the case that A is freaking equal to B. This is why it's important to follow the logical procedures and rules of proofs and not just be persuaded by, any argument that seems plausible. If A cross B is B cross A, then you could say that, oh, every first coordinate in this set would be equal to the first coordinates of this set, and since the first coordinates of this set are equal, then that means A equals B, since first in this one comes from A, and the first one in this one comes from B. And that seems like a really good argument if none of them aren't empty. But if they are empty, then we have a problem with that argument. This just goes to show that if you're doing a proof for any set, you need to take into account the possibility of one of the sets, or all of the sets, or any of the sets being empty. So now from that, we can have this little theorem here that says A cross B is equal to B cross A if and only if A is the empty set, B is the empty set, or A is equal to B. Over here I've written a really simplified proof for this. Case 1 and 2 are where A or B is empty. And case 3, we already went over case 3 where none of them are empty. So that's just to fill in the gaps over here, so A equals B. In general, when you're trying to answer a question, you might have a intuitive answer, or idea of what the answer might be, or how, or an idea of what the proof might be or might go. But it's only when you actually do the proof and do the repeated mistakes, find flaws, do all the other stuff, where you can be sure that your proof and your answer is actually correct. So now this leads us to the following definition. If P of xy is a statement containing any statement containing two free variables x and y, where x ranges over a and y ranges over b, then A cross B is the set of all assignments of 2x and y that make sense in the context of P. And so the truth set is the subset of that where P is actually true, formally over here. For example, suppose the statement P says x has y children, where x and y are obviously free variables. Then x ranges over the set, call it P. There's too many P's here. I'm gonna rename this to like C or something for children. Anyway, where P is the set of all people, and y ranges over the natural numbers. Since you can only have a natural number amount of children, you can only have 0 children, 1 child, 2 children, 100 children, you know what I'm saying? So the truth set of C is a subset of P cross N, where C is actually true for that ordered pair. A more familiar example of this would be the statement y equals 2x minus 3, where x and y range over the real numbers. All of the points x, y that satisfy this would be a subset of R cross R, or R2. And the graph of it would look something like this. So this shows that every graph you've ever seen is just a visual representation of a truth set of a statement containing two free variables. And in this example, this line right here is a subset of the plane. And although we've been only working with ordered pairs in this video, it is possible, of course, to have ordered triples or ordered, whatever. Ordered n tuples. This is what this is called. Where an ordered n tuple is just an ordered thing like this that has n entries. So for example, r cross r cross r, or just r3, is this entire space, the xyz space, that we've all also probably seen before. And this is just a visual way of representing this Cartesian product here, where every element of it is some ordered triple, like this. Anyway, that's it. Bye.